Here we have another example. Uh, the centroid of a circular sector right here. It is similar to the line of code, but here you can see if you need to find a centroid, you have two techniques. One, to move along the cross-sectional divide is you take a small angular region, like here the shaded region. If you see this thing, a small dr, and you can start from origin and move towards outward, and you can find your centroid. The second is to take a small region along theta d theta, and you can add this all arc and keep on adding to find these value of theta, find the value of centroid. Again, the important part is to define how you're going to find this area. If you, in this case, your area is simple pi r square. If you remember the area of a circle, cross-sectional area, so instead of pi you can have theta or alpha, 2 alpha, the 2 alpha r square is going to give you your uh, area or the overall area. But if we are saying a small area of the r, so it is defined as 2 r naught, that is the initial r naught, 2 times d r naught, that is the increment in r naught. This means r naught squared times alpha. Alpha is the angle you are going to move from. 2 is from two regions, that is above the center and the below the center, region 1 and region 2, right here, this part, sorry. uh, Now, so 2 comes from here. Now if you talk about the area, you have alpha, you have r, and then you have dr. This is going to give you the area of one half of the region, and multiply by 2, you're going to get the area region. Now why we need dr? Dr is going to help us to calculate the centroid as we move along this area. This is one technique to solve this thing. The other is simple, take a d theta, and this time it is again the same mathematics. You need to find how this area is defined. So this area can be defined as simple pi alpha r square, the whole area, the standard simple area, if you remember the area of the circle. But rather than in case of d theta, you need to take the projection along y-axis, that is xc, that is 2 by 3 r cos of theta. Now this is where you're going to move from up and down. 2 is from the two regions, and then you have cos theta. There's a projection along x-axis above and below, and 2 by 1/3 actually is 1/3 is basically based on the small triangle. This region is going to be 8. If you look at d theta and you take, say, d theta is very small, this will become a perfect triangle, and based on the symmetric shape of the triangle, you know it relies on 1/3 of its total height, and that gives you 1/3 of the cost of the length where the centroid of this triangle exists. We're going to add these small triangles to find the centroid of this big circle. Now, another example, if you go down, is a simple curve like this thing. And we can move along the same way. If we don't have the theta, we don't know the centroid does not exist. The center of this arc does not exist at xy origin. So we can move two ways. Number one, if we take a small slice and move the slice cross-sectional area along x-axis, or we can make a small area along x-axis and move it up and down along y-axis as shown here. And we can add all these areas and we can find the value of the centroid. Similarly, if we talk about a volume, we have the same volume function, and we can do the same thing, the same solution technique. If we need to find this volume, we take a small disk, and we know the cross-sectional area of small disk. And changing that area is through along, or you can say, based on this particular figure, as we move along y-axis, the area changes. This means dy has to take place. This means the amount of area has to be added, thickness has to be added, that is dy. As a result, the area increases. And we take these small slices of area, thin areas, and we keep on adding, we can get a volume. As you can see along in the equation, if we are adding along y to increase the thickness, where dy is a very small, infinitesimally small thickness. And if we move find out the value of r is x square, y square, z square. one R is given like this thing. The other, if you look at this thing, can be defined along x-axis and y-axis. So we have two R's. Now, this is how you would solve for one technique to find the value of the centroid of the volume. The other is to create a cylinder. This technique is not very interesting, but in fact, what you can do is look at the third technique. The third technique is you take this volume and you start looking up from the bar. You can say you take this volume and look it from the half section, the complete circle, and you're going to see a small theta variation like this thing, as we have done in the small a previously. This angle, that is the d theta, r d theta, it forms small triangles, small slices of triangles, and it is this whole triangle is going to create a single volume. And let's say this volume is very thin, thickness t, negligible thickness t. So you can find the exact shape, or you can say exact area of something. Let me draw it if I'm capable to draw it. It's difficult to draw without proper instruments. So like this region will become small area, and you start adding this area in a circular region all around the centroid, and you're going to find the centroid of the volume. These are the few examples taken from book. You can they are extensive techniques given. You can learn from these numericals as given here. You can find these numericals in the book, and in the end we are going to solve some questions within the problems of the book.